Again, welcome to basically the end of chapter 16. We're going to be doing problems with chapter 16 today and actually introducing chapter 17. For those who are sitting in for class basically 4B, there is a message that should be arriving in about 10 minutes. So hopefully you pay attention to that one for the ones who are sitting in 4B, the Wednesday class, okay, session. So the problems, I don't know if I communicated them earlier to you guys or not, are from the 15th edition. There was a question from another class actually about this problems, 15th, 14th, and all of that, basically difference between them. If you happen to have the 14th edition, you can still find the problems from Mastering Physics. When you go to the e-text version of the book, you're going to pull the e-text version of the book and go to where it says basically problems. Toward the end of every chapter, it says problems and discussion questions, okay? Look for those, click on that link for that specific chapter. So if I'm doing chapter 16, I click on that. And then basically go down, browse down until you find the problem. And in this case, I'm going to be doing problem 1639. So that's a quick way of finding it. If for some reason you're not sure where it is, just once you're in that link, just do Control F on Windows, or what is that? Command F, I think, on the Mac. That is going to take you to the search and find. Actually, you can do it also from search and find from the menu. And just click there, type there. For this specific case, you're going to type 16.39, basically 39. It's going to take you straight to it, okay? So if I tell you we're doing problem 39 from this chapter, we are doing chapter 16, so that's basically how you find your way through it. Again, I have probably the book in here somewhere for the 14th edition, so if you guys cannot find where these problems are, and if you happen to have a hard copy or a PDF version of your book and it's actually the 14th edition, please let me know also. We should be able to pull those from the 14th edition because these are common problems. They are not really unique to any version or any textbook or anything like that. Again, the main ideas from this chapter, from chapter 16, is that sound is a wave. It's not really a transverse wave like we saw it, for example, in the case for the waves on a string, which were basically going up and down, and the wave was traveling left to right. These are actually compressional waves. In other words, waves that the vibration is happening in the same direction where the wave is moving. So that is actually the distinction between the two. Other than that, these are also characterized by speed that is somewhat equal to, in this case, because the medium is different, the bulk modulus and the square root, of course. Not the tension, the bulk modulus over the density of the fluid or the liquid, the gas in this case, or Young modulus divided by the density of the solid, of course, under the square root. There was another formula that we used, or we found actually too, and I deferred that, actually trying to understand it for later on when we get into the ideal gas law, namely when we get into PV equal to nRT. As a matter of fact, we try to understand where the PV equal to nRT is coming from, and that's coming from the kinetic theory of gases. And for that, there was an expression in there that involved the square root of gamma times R. R is 8.314, which is the ideal gas constant, times the temperature. It's critical that the temperature is measured in Kelvin, not in Celsius, okay? As a matter of fact, once we move on from this part to the next part, which is thermodynamics, which probably the transition is going to happen today, we're going to be dealing with that concept, and it's a good idea, good practice. When you're measuring temperature, when you're calculating temperatures, you know, homework problems and everything else from this point on, don't use Celsius or Fahrenheit unless you are converting or you're asked to, okay? Use Kelvin. Kelvin is actually a good unit, and if you're not sure what is a Kelvin, just add 273 to the temperature in Celsius, okay? Again, this is stuff that is going to be from chapter 17. That's why I'm kind of a little bit hesitant on that formula, although problem that I thought that we should discuss, problem 70, is actually based on that formula, okay? Divided by the molar mass of the gas. If you look into any periodic table in a chemist, basically a lab or a chemist office or something like that, you will see the periodic table. On every single element, there is the molar mass listed there with a number, okay? for hydrogen, for helium, for all the elements in there, lithium, basically whatever you can pick up, magnesium, whatever you want to think of. That is the molar mass. That number there, one of them is actually the molar mass. That molar mass is listed in gram. The formula here requires a kilogram though. So in other words, whatever that number is listed in there, divided by 1,000 to find it in SI units, so use it in this formula. So this is the formula. Now you're asking what in the world is gamma, and you're absolutely right, because gamma is a factor in the square root and you have no idea where it's coming from at this point. And I'm going to tell you what it is. It's the ratio of the specific heat as constant pressure divided by the specific heat at constant volume. And both of these two concepts at this point are vague to us. What is the specific heat at constant volume and that of constant pressure? We're going to defer that discussion again to chapter 19 from this book, okay? So basically what it is gas can undergo different basically processes. You can fix its volume, raise its temperature by, for example, put it under a heater or a thing by basically putting it in a container, sealed container, so that no gas escapes or comes in, and put it under the furnace. And that way, basically, its temperature increases, like what you do, for example, on a pressure cooker, okay? Or that is at constant volume. Or maintain the pressure fine, but the piston now can go up and down on the gas. The volume can increase up and down, and the pressure needs to be in the same all the time, okay? So that is what the process in this case involves, constant pressure. You measure how much heat a gas takes, or a liquid takes in this case, in either of these situations, okay? You will find that that gas will take as much heat depending on the properties of the gas or the liquid itself, okay? That is what we mean for a single mole, okay? That is what we mean actually by specific heat at constant pressure and that at constant volume, okay? So that is the amount of heat, which is an energy at the end, taken by a gas at constant pressure for the constant pressure, or constant volume for the constant volume, per unit mole, okay? Per unit degree. You want the temperature to increase from what by degree, okay? Because it's going to increase overall. So if you let it exposed to a lot of heat over time, it's going to take a lot of energy. So you want just 1 degree, okay? So that is the definition, if you wish. So the ratio of that turned out to be a property of the structure of what's inside. Okay, it turns out that the monoatomic gases has a ratio that does not change. It's always 1.67. If it's helium, which is monoatomic, neon, monoatomic, argon, which is monoatomic, all of this are basically monoatomic gases. They're only made up of 1 atom basically per molecule. Helium by itself doesn't need anything. Those are the inert gases. And then you have the diatomic gases, like for example, hydrogen in the form of gas, oxygen in the form of gas, nitrogen in the form of gas. All of this are diatomic gases. Air, which is a combination of oxygen and nitrogen, which is also diatomic gases, that have that specific ratio. Gamma is always fixed to be exactly 1.4. So if you find 1.4, you know you're dealing with a diatomic gas versus if you're dealing with a monoatomic gas, okay? And again, if it's not in any of these two, it's probably polyatomic gas, like for example, carbon dioxide or water vapor or anything else. The number is different, it's around 1.3. So again, that's what goes in that square root for the speed of sound in this chapter, okay? So the whole thing is probably can be better understood down the road when we get into chapter 17 and 18, and especially 19. Then we probably can revisit this formula. But we will need this formula again for problem 70 because problem 70 goes about it. And it tells you gamma, take gamma, because they tell you specifically it's a diatomic gas in that problem, and they tell you to take gamma as 1.4. So if you don't know what that means at this point, which is you're entitled to that basically claim, just take the values. Just put the numbers, okay, in that formula and be done with it, okay? So you're entitled to that thing, but down the road you will not be entitled to that claim because you'll have to understand what all of these things mean. Okay. Again, problems I promised to do are problem 39. Let me get my notes in here. You guys have any questions for me? Good morning for the late arrivals. Okay, so what is my, okay, let me share. Close this window, I don't need it. Harris, are you sitting in a Monday Physics 4B or is it the Tuesday Physics 4B? Monday. Okay, you should have received a message right now concerning that class today, okay? Did you? If you're not sitting in the Physics 4B on Monday, ignore what we're talking. Okay, ignore what I'm talking about, okay? Anyway, so let me share with you the screen. Are you guys looking at where it says CH16 problems? Sometimes I have difficulty with this sharing thing. Yes, no? Okay, good. Good, so the sharing is working today for some reason. I almost used my laptop today because of the fact that this computer was tied up with basically uploading stuff to YouTube big time. So I'm glad this is this. So the problems I promised that we will do are problem 39, oops, 39, problem 43, problem 50, and problem 17. This is again from the 15th edition or the e-text. It's the same thing, okay? So, problem 39. Problem 39 tells you the following: tuning via a violin, okay? A violinist is tuning her instrument to a concert A note. So basically the A note, according to musicians, has to be 440 hertz. Anything higher, anything lower is not good. It has to be exactly 440 hertz, okay? So it cannot be 441 hertz. If it is, then the piano is, or at least the violin is not properly tuned, okay? So she plays the note, supposedly she's supposed to hit this note, okay? While listening to the electronic generated tone of exactly that same frequency. That frequency in here is a beat frequency. By the way, in the old days, we used to use tuning forks. Oh man, I did not produce any sound right now. Okay, I have a rock in here. Can I do it? I hope you guys heard the note. Did you guys hear it? Yes, no, maybe? Or it was kind of noise. Okay, Mike, I heard it, okay? Okay, according to this thing, and Harris also heard, good. So according to this thing, it's 512 hertz. It's the C note, okay? I don't know, if I bring it up close to you, you can see it or not, or it doesn't matter. So this is the C note. So if you are trying to fix the violin and you need exactly 512 hertz, the C note, this is what you need to sound like. Okay, so this is the sound for it. That's what we used to use in the old days. Now we have electronic devices, okay? We have electronic devices that do the same thing instead of this tuning forks. It's still, they're called tuning forks, okay? Excuse me. So she hits the note on her violin, and the note is also played by another instrument, which is supposed to be 440 hertz. What she did notice in this case is that there is a beat. When they arrive it to her ear, there is that hum, okay? She hears it, okay? Trained musicians, they can pick up that, they know that. And you would hear it too if you're careful enough. You would hear that there is a hum, that there is a frequency that is going to repeat. You will hear that note, but you will hear at the end, and then it's going to repeat, and you can find its frequency. So what you notice that the beat frequency in this case is 3 hertz between the two. Of course, the period, if you're curious, is about 1/3 of that. It's about 1/3 of a second. Okay, 0.3 seconds. So it's going to repeat 3 times every second. Basically, that's what that means. Which increases to 4 hertz when she tightens her violin. So now she needs to tune her violin because it's not exactly 440 hertz. What she does is there is actually tension under the violin, so she tightens it. The string was a little bit loose compared to what she did now, so she tightened it. And then what she did again, she hit the note again. But now, instead of going closer, so that basically the distance is less and less, it has actually increased. It's 4 hertz now. Okay, so the period now, there are 4 beats in a second now. So that means the frequency now is 4 hertz. So the second time, so this is the first time. The second time, the beat became at 4 hertz. So the question is, what was the frequency of the note played by her violin when she heard the 3 hertz? Obviously, it was not 440 hertz. If it was 440 hertz, this frequency would be exactly 0. They come exactly in sync in her ear and she would not hear anything. So it's either 443 or 437. Those are the only 2 options, because the F beats actually, it's either ahead or above the other one. So it's actually the frequency of one minus the frequency of the other. Let's call this one, for example, the electronic device that we know is beating at 440 hertz. This one is properly adjusted electronically. This one is her violin, okay? So the violin in this case, either higher by 3 hertz or lower by 3 hertz. But when she tightened it, it actually increased, okay? It went to 4 hertz. It did not go down. Obviously, this, if I take it in absolute value, theoretically, it could have gone to 444 hertz, or it could have gone to 436 hertz. It's still the same difference in absolute value. But the trick here is that she tightened it. She did not loosen it. Okay, that means now the tension in the string is higher. Since the tension is higher and it's standing waves, actually, those are because both ends of the violin and the string on the violin are fixed. So this is actually a fixed end. So whatever that note is a standing wave there, okay? And the properties of the standing waves, if you guys remember it from the lecture, you can find ever the standing waves. When I have a string, actually it's from the previous stuff when we did the string, because this is a string actually. Although it's a combination of sound and violin, where it's the violin in this case are transverse waves. So let me go back into chapter 15 now. I believe, yeah, here is a standing waves. So lambda is in general a fixed number of length divided by n. What is the standing waves expression? No, we're still way back in here. Okay, here is the expression. It's 2L over n. Okay, so when she tightened it, so that's lambda. Remember the speed of the wave, we found it also to be square root of the force, in this case the tension, divided by mu. She did not change the strength, so mu did not change, okay? And lambda times the frequency is equal to the speed, is equal to square root of f over mu, okay? So the frequency then must be equal to 1 over lambda, and 1 over lambda is just n over 2L, times the square root of f over mu, okay? So this is the expression she's dealing with now. She made f higher by tightening it, and you have to look for the word in it, she tightened it. That means she increased the tension in the string. That means the frequency went up. She thought that maybe she was at 437, and if she increases the tension a little, she's going to bring her closer to 440. In doing so, actually, it made her further away. So actually, her tension, her frequency was higher than 440 hertz. So when she increased the tension, instead of staying at 443, she went to 440 hertz. Do you guys understand what the problem is? Okay, very good. So basically, here is the deal. Her situation is this is her conundrum, if you want to call it a conundrum. She thinks her frequency, either this one or this one of the two, because she can hear the 3 hertz clearly the first time around. So she made a hypothesis. I believe it's this one, because I know the frequency is equal to n over 2L times the square root of the tension over mu. She cannot change n, because that's the note, actually. That's the mode she needs to operate with. She cannot change the length of the string. That is actually the manufacturer who made the violin for her. She bought it, she loves it, and actually she even have her name as probably written on it. So she's not going to change the length. She's not going to change the string in this case, because the string actually is fixed too by the manufacturer. The only thing she was provided is a tensioner on the string. Either increase the force, the tension, by making it tighter, or loosen it a little bit. So now, if she increases the tension, she wants to bring it from 437 down to exactly 440. So that's what she's thinking. She's thinking maybe it's here. Okay. When she increased it, she expected this difference to be less, actually, but what she ended up was higher. So what actually she was at this number. She was at 443. So indeed, when she increased the tension, her violin now is operating as 444 hertz instead of what it was before. And now the beat she hears is actually this one, 4 hertz. Makes sense, hopefully, for everybody now. So if you're going to be piano tuning person, you know exactly what they do. This is what they do, okay? So what was her frequency? What was the question A? What was the frequency of the note played by her violin when she heard the 3 hertz? It was, based on this reasoning, 443 hertz, because when she increased the tension F, okay, the beats frequency increased, okay, and did not decrease. Okay, so mainly that she was dealing with F beat, yes, equal to her piano. This is the violin, sorry, sometimes I mention piano, minus the note in here from the electronic device, which is supposed to be 440 hertz. So this number went up by 1 more. So her piano was 443 to give me 3 instead of 437. Okay, part B. To get her violin perfectly tuned to concert, note A, should she tighten or loosen her string from what it was when she heard the 3 hertz? What do you guys think? Should she loosen now the string or tighten it to bring it to exactly 440 hertz? What should she do? Come on, this is not a democracy. Either one or the other. Either loosen the string or tighten the string. What do you guys think? I should have that sound that they do on TV for games, you know, when a person is given like 20 seconds to answer a question. What do you guys think? Okay, she tightened it, the beat frequency increased. What should she do so that the beat frequency doesn't increase? It goes down actually to 0. Loosen it or tighten it further? So that's the question. Okay, Harris at least thinks that she needs to loosen it. How about anybody else? How about the other guys? What do you guys think? Okay, yeah, okay, so there is a consensus now. So yeah, she needs to loosen it, so that means bring F a little less. If F comes in a little less, where everything else is the same, then F will come a little less of her violin, and now this difference will be less and less, so that at the end she will end up with a beat frequency of 0 ideally, so that you can get the violin. So the answer, yes, needs to be loosened. Okay, I don't know if I spelled it correctly or not. Okay, the thing with it is the tension needs to be less. Okay, so she needs to go in the other direction. Now again, please don't be, I mean, sometimes, and not sometimes, a lot of times actually your first guess is actually correct. Okay, so don't doubt yourself, because it's correct in this case. Okay, and a lot of these things are really common sense when you think about them. Sometimes if you don't think about something, it sounds kind of strange and out of the place. But then when you think about it, it becomes obvious. In this case, we have to really do the F go down in order for this one to stay there. Okay, this is problem 39. It's a fun problem. I like this kind of problems. Problem 43. You have, so the next problem that we're going to be doing today is 43. So this is 43 now. Okay. Problem 43 says 2 trains whistle. Why do they say 2 trains whistles? A and B. Okay, 2 trains, A and B, whistles, each and every one of them with 392 hertz, okay? So I have train A and train B, and both of them have the same whistle, basically, of 392 hertz. Both of them have the same frequency, okay? Exactly. And A is stationary and B is moving toward the right from A at a speed of 35 meters per second. Okay, so here's train A. And here is train B. Train B, A is not moving. Train, let's call it BA. VB is equal to 35 meters per second in this direction. Okay, away from train A, okay? A listener is between 2 whistles and is moving toward the right with a speed of 15 meters per second. If you look at the picture, you will see that the listener is here and is moving in this direction with a speed of 15 meters per second, okay? They are both moving away from the train that is stationary in the station. Okay. No wind is blowing, so good, we have nothing else to worry about. What is the frequency from A as heard by the listener? So the listener is moving away from the source. The source is emitting a frequency F. This one, by the way, is emitting the same frequency, and F is equal to 392 hertz. Both of them are emitting the same frequency. But from this vantage point, the listener will hear a frequency from A that is equal to, basically, the source is not moving. So we don't have to worry about the denominator. It's V of sound. So this is the V of sound. I'm going to check, did they give the V of sound in this problem or not? They did not give you the V of sound. So I'm going to take V to be 443 meter per second for sound. So again, if it's not given to you, please ask for it in problems. And if not, just take around 440 meter per second. So this is basically sound speed. Okay, so it's this value. Now, since the observer is moving away, the frequency is going to be less, and it's going to be V minus VL in this case. Okay, it's a numerator. Remember, the numerator is always the observer. The denominator is the source. The source is not moving, so I don't have to worry about the denominator in this case. So the question is, what is this frequency as the listener will hear it from the other one? So it's going to be less frequency because he's moving away from it. So it's going to be FA is equal to 443 minus his speed, which is 15, divided by 443 times the frequency, which is 392. So it's simple algebra in this case. So I'm going to basically, let me see if I don't have my calculator going. So let me get mathematics. Please do this algebra in here because I tend to make mistakes in here. So please fix these things. I always make mistakes with signs, and sometimes I even powers, and sometimes with all kinds of things, especially when you're teaching, trying to explain things, and you get entangled in some ideas and you forgot to something in here that makes everything go completely wrong. So like a parenthesis right now, 443 minus 15, I could have done this in my head probably, times 392, but divided by 443. Okay, so it's telling me it's 378.7 or 379 hertz. Does this make sense? It went down, and it does, because he's receding away from it. So he's going to hear lower and lower, basically pitch, in this case, lower and lower frequency. So that is typical, that is fine. If we find it more than 392 hertz, we have a problem. The guy is moving away from the source, so it should be less frequency, okay? So in this case, it's less frequency as far as is concerned, okay? So that is this part. Now, that's question A. Okay, for those who came in late, we already did a problem, okay? So you need to really check at least the recording up to this point, which is a half an hour up to this point, okay? Your job today is actually to check all of these numbers. So that is the item of the discussion today, is verify and check and calculate this, all of this, okay? So whatever these problems we're doing, that is basically what you're supposed to be doing, okay? So don't think that the fact that I'm solving these problems with you guys and we're going through them all together means that they are basically immune from mistakes. So you have to really go and fix all of this and go through the steps yourself. Make sure you understand how we went from one step to the other, to the other, to the other. If in case you have a problem similar to this one down the road in an exam or something like this one, you don't have to, oh man, I forgot the next step. I have no idea. I saw it somewhere in a video, but I have no idea which video that is. And even if you go to it, then probably it's still not vague to you, and you have no idea how to tackle that specific problem, which is probably somehow the idea is related, but the questions are more different. So you need to hammer these things, and you need to go through all of these problems that we do in class together so that you guys are comfortable with the other problems and you are at ease with them, okay? Makes sense how this thing is working for you guys? Okay, good. Please take that into account, okay? Don't rely on me doing things. You have to do these things on yourself. In class, actually, what I do, if we were face-to-face, I don't do these things. I ask in rotation, everybody will go to the board and solve the problem, and they will tell me, I don't know how to do it. It's fine. We're going to work together through it. and that person will be the best served person in the class because he or she did the actual problem by hand in the class. Okay? Worked, basically wrote the stuff. And then it's going to be the turn of someone else and the turn of someone else and the turn of someone else. Unfortunately, we're not there in here, so we're doing it online. That's basically the best we can do at this point. Okay, so let's continue with the question B. Question B is, what is the frequency from B as heard by the listener? So now it's a different situation. The source is moving and it's receding from the observer at the speed of 35 meters per second, whereas the observer is moving toward it, okay, towards it. So now for part B, the situation is different. So the frequency perceived from B, as far as he or she is concerned, is the following. It's still emitting at the same 392 hertz like the other one. So train B is emitting at the same frequency. But now, the numerator is always the observer, or the listener, the denominator is the source. The observer is moving towards the source. So the frequency should be increasing, and it's increasing with the velocity v of sound plus the velocity of the listener. So it's increasing from FB by this amount. However, the train is receding, the source is receding from him, so it's also decreasing. And if I divide by a number for me to decrease it, I have to add actually, okay? Since it's receding, it's a plus. If the source was approaching, it's going to be a minus, in which case the number will be less. When you divide by less, it's going to be higher. But ultimately, as you can clearly see, the source is moving faster from the listener than the listener is approaching it. So in a sense, there is a net separation between them. There is a net distance that is increasing over time. So the frequency actually should be also lower. It's clear for the first case between train A and the listener that the distance is increasing. So the frequency went down from 392 down to 379. For the second one, the train is not sitting still. The train is actually moving. So the fact that he is approaching it is going to compensate for some of those decreases, but by how much? The net thing is not going to be effective. It's going to decrease anyway because there is a net separation between them. Okay, there is a net. The train is moving 35 meters per second, whereas he is approaching at a 15 meters. So there is a net difference of 20 meters per second in this direction. So let's see in this case what the calculation will give me. From train B, this is what the listener will hear. This is 392 again. So the speed of sound is 343. Did I use 400 or 300? Oh man, did I use the wrong number? I think, yeah, 443. Oh man, now I'm confused. So what is the speed of sound in air? You see, you use it a million times, but when you think of something, it becomes an issue. What did we say the speed of sound in general has to be in the calm air? Man, that's not good. Three hundred, not 400. Sorry about that. 343. That is not good. That's not 400. That's too fast for sound. It's 343. Okay. So I used the wrong numbers in here. Again, you're supposed to fix these things for me, please. Okay. 300. So we need to recalculate this thing in here because it's not correct. So that is what I'm telling you. That is exactly my point. Hopefully you guys got it. 343. So let me go back into the formula, just fix the numbers in there. Come on. Oh, I double copied it. Okay, so this is 3. And this is 3. It's actually 374.8. So the correct answer is 375 hertz. It still went down, and that's how it is expected. Okay, it went down to 375 hertz from 392. This is from source A. Now we also expect it to be less than 392 in this one too. Okay, so again, plus 15 divided by 343 minus 35. Okay, I'm going to use the same formula, except now I have to fix the denominator correctly. So it's the numerator, first of all, it's a plus. In this case, it's not a minus. And the denominator will have a plus also in it, but 35. So the answer is 371 hertz. As expected, also, this one went down too, okay? Because the train B is receding from the observer more than the observer is approaching this, the train. That's why the frequency went down from 392, perceived to be of lower frequency, basically, a lower tone, basically, in this case, deeper voice, if you want to, okay, versus a sharper voice, which is higher tone, higher frequency that is emitted by the source. It may not be that much, but you are going to notice it. You're going to hear it, actually, okay? If all of a sudden, the other train starts to move 35 meter per second, which is going to gain speed on him, he's going to hear higher and higher frequency than 392. That's an interesting application. You guys can pick up that one, okay? You can see it and see it at work, okay? Anyway, so that is frequency of B. And what is the beat frequency in this case? So he's going to hear a hum, actually. He's going to hear both frequencies, but he's going to hear a hum. So that's C, frequency of beats that he's going to hear, the humming that is between them. So it's the absolute value of the difference of the two numbers. What was it, 74 or 75? 75. So it's going to be 5 hertz. I mean 4 hertz, I'm sorry. He's going to tell the two trains. Actually, it's going to be an annoying sound, but he's going to hear it. Does this problem make sense to you guys? Okay, very good. You have to be careful in here in the formula. Again, let me write the formula for the Doppler effect. The frequency perceived, this one, is equal to something something the frequency emitted or transmitted. This is the source. And there is a ratio in here. I have to have the velocity of sound in either case, okay? Now, if the observer is moving toward the source, it's going to be a plus. I have the velocity of the observer in here, and I have the velocity of the source in here. I need to decide on my plus or minus. If the observer is moving away, like in this case, A, moving away, in the second case, moving towards the B, then the second case is plus, and the first case is minus. Now, if the source is moving towards, then it's actually a minus. If the source is moving away, it's a plus. If you can resolve this, a lot of these problems will be clear for you. You are not going to have a problem whatsoever. Basically, the bottom line is the frequency will increase if you come closer. The frequency will decrease if you get higher and higher, I mean, further apart, recede between the listener and the observer. Okay, so this is basically what I've used for this problem so far. Obviously, the beat frequency in this case is just the difference between the two frequencies and its absolute value. You don't care about the sign. Okay. So that answers problem 43. Problem 50. Okay. It says, the siren of a fire engine that is driving northward at 30 meters per second emits a sound of frequency 2000 hertz. Okay, so the train, what is it? No, it's not the train. What is it? Fire engine, okay? Fire engine has a frequency of 2000 hertz and moving in this direction. That is northward, okay? So of 30 meters per second. So V of source is 30 meters per second, okay? So it seems like we have 3 sig figs. A truck in front of the siren is moving at 20 meters per second. So here is the emergency vehicle. Here is the truck. The truck is moving with 20 meters per second. And it's in the same direction also. Let me read it again. The truck in front of this engine is moving northward also, just like the other one. So the direction north for me is going this way, okay? You can draw it up if you like, but that's the same thing, okay? But this velocity is, so there is a net gain now. You guys see that? The distance is shrinking between the emergency vehicle, between the fire truck and also the regular truck. The distance is shrinking. So the frequency now as perceived by the truck should be higher frequency. But let's see what they are asking first before we start making any assumption. What is the frequency of the siren sound that the fire engine driver hears reflected from the back of the truck? Here is the deal. This sound, which is a wave, by the way, will come in here and hit the truck, and now is reflected from the truck, and the driver will hear that reflected wave now. So what we have in this case, we have the F source. When it's received in here by the truck, it's going to be shifted. So this is the first that is shifted. And this is, I'm going to call it F reflected because it's going to be reflected from the truck. So this is the F reflected, and it's shifted from this F frequency in here. So from this expression here, I can find this frequency that is reflected times the F. And since I have the velocity of sound for either case, okay? Now the truck is moving away. So expected in here a minus sign. When it's moving away, it's a minus sign. When you're moving towards, it's a plus sign. So it's a minus V of the truck, but the source is moving towards it. When it's moving towards, it's a minus also. It's the first sign in the numerator, in the denominator, I'm sorry. So that is V of the source. So this frequency now, as perceived by the truck, there is a net gain in this case, so the frequency should go up, okay? So if I do the calculation, this should be equal to 343 minus the velocity of the truck, which is 20, divided by the velocity of sound, which is 343, minus the velocity of the source, which is 30. This time is 2,000 times 2,000. So I expect this number to be higher than 2,000. So the frequency in this case, that is reflected. This is reflected, not heard yet by the driver. This is still just coming off of the truck, okay? So now it's going to be shifted again by the time it comes to this one. So this is not the total frequency, this is just part of it, okay? So maybe just, if you wish, I don't really need to calculate this number. I could leave it symbolically and write the other one in there. So by the time, but it's interesting to see the number in here. So let's see in here quickly the number in here, because I expect this number to be more than 2,000. So 343 minus 20 times 2,000 divided by 343 minus 30. And of course, indeed, it went up 2063.9, 2064 hertz, okay? 2060 hertz, okay? So it went up by 60 hertz, basically, so as expected, okay? So, but that's not really the question that they are asking. They are asking the question as heard by the driver. So now from the vantage point of the driver, as if this back of the truck is acting as a source now with a frequency FR. So as far as he's concerned now, he's going to perceive this frequency as shifted from FR. So he's going to call, let's call it F prime, okay, as heard by him. And it's going to be, again, the FR in here. This is the source now. So the reflected wave becomes the source now, okay? And now, as far as he's concerned, he is the observer. The truck driver is the observer. So his velocity now is gaining velocity on the source. So it's going to be a plus since he's moving toward the source of the reflection. So it's going to be plus the V of, I'm going to use the symbol S because it's the same thing in here. So this is actually the listener whose velocity is that of the 30, basically, okay? Whereas the source in this case, okay, is moving away from him. So the frequency is actually going up also. I mean, going down because of that fact. So it's going to be a plus also. So when the source is moving away, it's a plus in the denominator. So it's again velocity of the source, which is actually the listener. So the velocity of the source now, which is actually that of the previous listener. So that's where the 20 need to go. If I plug in my numbers, this is how f prime would look like. F prime is going to be equal to, again, the numerator, as I started writing, is 343 from the previous one. Because I'm going to replace the value of FR in here. First of all, 343 plus 30 divided by 343 plus 20 times FR. FR has an F in it, the beginning, the starting one at all. So it still has 343 minus 20 and 343 minus 30. Listen, I expect this frequency to be higher because of the following thing. This guy is moving 20 meters per second, moving away. The fire truck is moving at 30 meters per second. So the fire truck is gaining more and more speed on the other one. So the pitch now needs to go higher naturally. So that although the reflected wave now, the reflected sound now is going to be heard by him, but he's going to be higher than the initial 2000 frequency because there is compression, there's distance is less and less. So let's plug in the numbers and see if indeed we get that, okay? So I expect this number, this is 2000, by the way, this is the original one. So let's do the math in here. So what we have in here, we have, of course, you can do some algebra, numerator, denominator. So 343 plus 30, that's 373, times 343 minus 20, that's 323, okay? Times 2000 divided by, open parentheses, 343 plus 20, that's 363, times 343 minus 30, that's 313, okay? And what is the number? 2120.7 or 21 hertz. So indeed, 2121 hertz, because we actually have 3 sig pigs only in the problem, so it's 2120 hertz, which is more than the 2000 hertz, as expected. I know it's kind of dizzying at times when you start thinking about this situation, reflected versus which one is moving. You have to be meticulous. You have to know exactly where the source is and where the observer is. In this case, they flipped roles. The source, the original source, became actually a listener. And the listener, the original listener, became the source because of the reflection. Okay, so that's why the roles have been flipped in the second term. That's all. If that's the case, then you're in good shape. Okay. Does this conceptually make sense to you, at least? The fact that the distance is shrinking, the frequency has to increase no matter what. And the fact that the reflected wave now becomes actually source for the observer now, who is a driver sitting on the truck, the fire truck. Yes. Think about bats and how they move at night. Bats don't see well at all. They don't see hardly anything, but they use their sound, and a bunch of them swarming coming out of a cave, and none of them hits the other. I mean, forget about the walls. The walls are stationary, so the sound that reflects from the walls of the cave, they're going to hit their ears, and they're fine. They can detect that that is an immobile object that is fixed in space. But how about the other bats that are moving all over the place? So the sound coming from them goes and hits them and comes back, and they can tell exactly how to navigate their way to get into their fruit tree, wherever they need to go to. Okay? Or when they come in the later on also to the cave, so that they don't bump into each other and have a lot of accidents. They use this. They use the Doppler effect. They know exactly which way the sound is increasing, which one is decreasing, which batch is moving towards them, which batch is moving away from them. Not only that, how fast, when to duck, when to move this way, when to move that way, and when to go this way. Isn't this interesting? Make sense? Okay. Listen, think of bats. I mean, they must have taken physics 4C and learned about this Doppler effect and do all of these calculations on the fly while they're actually, literally speaking, flying. Okay? Otherwise, they're in trouble. Oh, they asked about the first frequency. I'm sorry. I missed question A. What is the frequency of the siren sound that the fire engine driver hears reflected from the back of the... Okay, so we answered that. That's part A, I'm sorry. What wavelength would this driver measure for this reflected wave sounds? Okay, the driver should not really be confused. He or she knows exactly what this wavelength is. The wavelength is equal to, so that the speed of sound is always equal to the dispersion law, the frequency times the wavelength, okay? So from this one in here, we can find the wavelength as perceived by the driver, which is just V over F prime, and V is 343, and F prime is 2120 Hertz, and that is equal to, divide the two numbers, okay? So it's going to be 343 divided by 2120, and that should be 0.16 meters, 16 centimeters. Okay. The original frequency, by the way, the original wavelength was V over 2000 F. So that was 343 over 2000. And that was actually a longer wavelength. Let's see here. Oh, I'm sorry, shorter because longer because it's a lower frequency. So it's going to be 343 divided by 2000. That's indeed 17 centimeters. So the frequency, the wavelength has shifted toward shorter wavelength, higher frequency. Okay, so this is the original one that the fire truck is emitting, 17 centimeters wavelength. Now, by the time it's reflected, it's back to 16 centimeters, meaning the frequency went up. Okay, so this is the problem, problem 70. And finally, problem 70, that was problem 50. Okay, so this is problem 50, the one that we had a discussion on. Problem 70. Please verify everything again. So this is for this problem. So far we did 3 of them. Hopefully we still have plenty of time to do problem 70. So a long closed cylindrical tank, that's problem 70, and that's the one I made a big fuss over in the beginning about that formula for. Basically, the velocity of sound is equal to square root of gamma r t over m, the molar mass. Gamma is the ratio of Cp over Cv, and you don't care for it at this point what it is, it's given to you. It's just a fixed number, 1.40. It has no dimension, it has no units. It's characteristic only of this materials. Since they tell you it's diatomic, actually, that means gamma is 1.40. So if you calculate and everything, and at the end you find the value that is gamma equal to 1.4, you know that that gas is diatomic. If it's a hydrogen, H2 or O2 or N2, or basically one of those diatomic gases, okay? R is a constant. R is just basically 8, that's right, R 8.314 joules per Kelvin per mole, okay? Again, PV equal to nRT. Did some of you take chemistry before and learn about PV equal to nRT or not? If you did not, don't worry. You're going to learn it in the next 2 chapters. Anybody? You guys didn't take this in chemistry sometime, either in college or in high school? Okay, at least one of you guys did. So this is actually in Joule. This whole thing is in Joule. This is work, actually. And this is also must be work. This is in Kelvin, not in Celsius, not in Fahrenheit degrees, but must be in Kelvin, unit for it. N is just a number of how many moles you have in the gas in this case, okay? And R is that constant. This is experimental law, basically. This is what experience has shown us. So that is what R is. M, again, as I referred to at the beginning, is the molar mass, which is something you can look up in the periodic table and see, except that that one is given in grams per mole. What you want in this case, you want it in kilograms. So whatever with the periodic table is going to tell you, you need to multiply that number by 10 to the negative 3. That's it, to get it in kilograms. Because otherwise the expression doesn't make sense. As you can clearly see, gamma has no units, R has the units of joule per mole, which is just a number in this case, so forget about that one, it's just a number, per Kelvin. Kelvin cancel Kelvin, and I have a joule in the numerator, and the joule in the numerator is force times distance, and force is kilogram, mass times acceleration, times the distance to get it in joule, divide the whole thing by kilogram, cancel the kilogram by the kilogram, and now I have a square root of meter squared per second squared, which is exactly what it needs to be as a velocity. So if I square meter squared per second squared, I have the velocity as it needs to be in units. If I have this guy in kilogram, if I have it in gram, now I have a problem because this is in kilogram and that's in gram and they don't cancel. So for me to use this formula correctly, I need M to be in kilogram. That means whatever the periodic, whatever the chemists tell you, you have to divide it by 1,000. Don't trust their words in this case, okay? You have to divide that number by 1,000 to get your units fixed correctly, okay? So they give you a table in here, and the first thing you notice is the temperature is actually in degrees Celsius, not in so I'm gonna get Excel going and open things in Excel. Before I do that, let me try to answer some of the questions, because the first question in here is that, okay, remove, is, let's see what they say in here. So they gave us a data in here, T negative 20 degrees, 0 degrees, 20 degrees, 40 degrees, 60 degrees, 80 degrees, increments of 20 degrees, okay? And the velocity of sound in this case is measured in meter per second, and they gave you the values in there. Explain how you can plot this result so that the graph will fit by a straight line. We want a line. So what we're given in here as the independent variable is T, which we need to convert to Kelvin, because they gave us in degrees Celsius. So we need to add to it 273 to make it in Kelvin, okay? Because again, this expression needs Kelvin in here. It's not going to work with the degrees Celsius, number one. And they gave us also the velocity now, which is the other side in there. And they want us to plot it in such a way it's a straight line. In order for it to be a straight line, I have to square this thing. If I square it, then v squared will be function really proportional to t, which is going to fit in a perfect line. So I need to square v, whatever they gave us. So we're going to write v squared, then it's equal to gamma r over m times t. So t now, properly converted, should be the perfect thing for us. So we're going to take the data as they gave us. Write the temperature instead of degrees Celsius, write it in Kelvin, and square the velocity and plot the graph, okay? Because they said construct this graph and verify that the plotted points do lie close to a straight line. Then B, because the gas is diatomic, gamma is equal to 1.4, so they gave us exactly gamma to be 1.4. Use the plot of the line in part A to calculate M, the molar mass of the gas, express M. So if I know the slope, let's call this one slope, because that's the slope that we're going to get, okay? If I know the slope, then in this case, this data is going to be basically obviously, I'm sorry, there is another thing in it. If I don't convert in here to degrees Celsius, all I'll be doing is just shifting that value in there. That's it. So we're not going to worry about that point. So we're going to have a plus y-intercept, okay? But since we're going to shift that, we're going to be fine. Okay, so if I find the slope from this expression, I can find m or gamma r over m equals to the slope, in which case I can find the molar mass m. It's going to be gamma r over slope. The only problem in here is that this m is going to be in kilograms. So if I want to compare it to anything in the periodic table, I better make sure that to divide by that number or multiply this number by 1,000 to convert it back to a kilogram, to grams. And now look at the table. Okay, after that, look at the table. So this is the formula which we're going to need. This is basically what we need to in here. Let's go to Excel in here. Let me stop sharing the screen and share with you Excel now that they just opened, if I can find it. Where is my Excel? Here. Okay, I hope that you guys are looking at Excel spreadsheet. So in here, let's look at the independent variable. First of all, the values that they gave us, T in degrees Celsius. Okay, so it's minus 20. And I want us to basically add 1, 2, 3, 4, 5, 6. So 2, 3, 4, 5, 6. Okay. So we're gonna do the autofill in here. Where is that? Fill to the right. No. Fill series and the row, and we add to it 20. Okay. So that's basically quickly in here. So one way of doing it. Okay. So I need T. Oh man, I should really write it as an x-axis, don't I? That's not good. Sorry, bad. Okay, let's fix that. Okay, so it's a negative 20. I want to write it as a negative x-axis, so all the way to 7. Is that correct? So now I need to do the same thing. Fill series, and I need to decide. Actually, it's a column and units of 20 degrees added. So again, we did the same thing. It's good. Okay, so we have T in. So now I need to write T in Kelvin actually, because I need T in Kelvin. So it's going to be equal to this cell plus 273. And we're going to do the same thing for all of the other quantities. So this is basically the temperature now in Kelvin. Okay, so we're good. Now the velocity V as given to us in meter per second, which is exactly the unit we need really, meter per second. So there is no conversion for this one. They said that the first one is 324. The second one is 337, I'm sorry. And the third one is 349, and 361, 372, and 383. Okay, good. But we need the velocity squared now, we need the V squared now. So then we're going to equal to this number squared. So Control C and copy and paste. We're in business now. Oops, what did I do? C2 squared, C3 squared, C4 squared, C5 squared, C6 squared, C7 squared. So everything looks good now. Okay, so we're good, because I was worried that maybe the formula has shifted on me. Okay, now I'm going to plot this as the x-axis and hold the shift key, I mean, not the shift key, the control key, and select this cell. I'm sorry, no, actually, the T in Kelvin again, you see? I almost did it. V squared as a function of T. So we're gonna go in here and insert. So we want V squared as a function of temperature. Temperature is measured in Kelvin, not in degrees Celsius, as I was going to do in here. I'm gonna come in here, insert this chart in here, and as you can clearly see, it's a line, as it's supposed to be, okay? So actually, I don't need that. I can do the data one if you like. So again, insert data with the data points in here. So I need those data points to see exactly what I'm talking about in here. So Again, I could do a fit line. I could do whatever. I can move this in here to a move chart to a new chart, and basically have the chart in here looking at it. Now, what I need from this chart is actually the trend line. And that should give me the linear and actually more options in here. And more options, I want to display the equation on the chart. This is the equation. This is the slope, by the way, 416. That is what I need from this expression, 416.5. Okay, that is the slope I will need. So let me go back into the Excel spreadsheet in here, and I could write in here the slope, okay, equals to slope, and I want to find the slope. It should be the same number as we did earlier. So we need the y components. The y-axis is this one, actually, comma. We need the x-axis in here, and here is the x values in here. So we want that slope, and it's telling me exactly what that fitting was telling me. So first of all, to answer the first question, is it really as predicted as a line? It is a line, okay? If you're not sure, just pick up the R squared and see how fit it is. It's 99.99% sure that this is a line. Okay, there is 0.01% error that it might not be a line. And because that's the data, actually, you're trying to fit it. So you're not going to get it exactly 100%. Okay, so this is the slope. And we want M now. So this is the slope. We want M now. If I go back to the formula, if you guys remember, M is equal to gamma times, what did we call? Let's call this one slope. Okay, and let's find the gamma. The gamma was 1.4. So we're going to call this one gamma. And finally, we have the R, constant R, 8.314. Okay, let's call it the value R. Okay, R constant. Okay, so now we come into this formula and write just that formula, equals to, remember, it's gamma times R constant, which is really, this is the one that constant, divided by the slope. Okay, and that is the value, 0.00, except that this is in kilogram. We have to convert this guy into grams and look at the periodic table. So M, this is in kilogram. Obviously, I have too many sig figs in here. I only should have 3, okay? So it's 0.279, that's all I need in here, okay? So I cannot really make up more sig figs than I can have in here. So M in gram, which is the one that I need to compare to a periodic table, is equal to this value times 1,000. Because if that's how many kilograms, it is 27.9. And if I look at the periodic table, a diatomic gas, because gamma is equal to 1.4, and they tell you specifically it's a diatomic gas, whose molar mass is 28, meaning 28 divided by 2. If I look at the periodic table, that is nitrogen. So this is nitrogen gas. Okay, this is N2 actually. Okay. Let's see what the questions are. Use the slope of the line, calculate M, the molar mass of the gas, express M in grams. What type of gas is in the tank? That is nitrogen gas. Make sense to you guys? I know I'm verbose in the solution. I know I tend to explain probably sometimes more than needed, and it may be too much explaining, but I really want you guys to go through this whole thing and understand the process in here, okay? So basically, I know this problem, out of fairness, we still did not really get into the gamma, what it means. We don't get into PV equal to 1 RT from a physics perspective, what it means. But the molar mass, probably some of you did not have chemistry also, they don't know what that is. But if you go to a periodic table, you look at any element, you look at nitrogen, you will find it 14 grams. 14 basically, that's its mass in there, atomic mass, what do you call it? Atomic mass, yes, 14. That's 14 protons basically, each proton is 1 gram, okay? 14 grams. Now you need to convert that into a kilogram to use it properly, so you have to divide it by 1,000. If you find it in kilogram, like what we did, you have to divide it by you have to multiply it by 1,000 in this case to get it into grams. So we found it, but we found it diatomic. They tell you specifically in the problem, if you look at the problem 70, a long closed cylindrical tank containing a diatomic gas. So we know it's made up of 2 atoms that add up to 28, 27.9. Okay, so 28 divided by 2, that's 14. If you look at the periodic table, carbon is 12, oxygen is 16, and right somewhere in the middle is where nitrogen is, okay, 14. So this is nitrogen gas, and nitrogen gas is diatomic, is N2 actually, just like oxygen, O2, just like hydrogen, H2, okay? But how did they get that? I get it from the slope, because V squared is equal to square root of gamma RT over M. And they gave me the data for this V, basically, which I had to square. They gave me the data for T, which I had to properly convert, okay? So we did that work. And then the expression gave me a value in there for the slope. I used that because I didn't know what M was. They didn't tell me what the gas was. So I did that to find what the gas is, and we found it, okay? So that is basically, so if you're worried about that y-intercept, why in the word we have y-intercept, this formula doesn't work all the way to that. Basically temperature T equal to 0 Kelvin. It doesn't mean anything, so don't worry about that number, okay? First of all, you cannot get T equal to 0 Kelvin. We'll have this discussion down the road. Actually, we'll have it in next chapter. As a matter of fact, we have about 5-6 minutes. Probably we could introduce the next chapter, which is chapter 17. It's about temperature and heat, okay? Okay, so the items of the discussion today is redo the calculation, check the numbers, check the analysis, make sure it makes sense to you and you're comfortable with it. Spend as much time as you need to understand these things, because it will have implications on your exams, implications on the course in general. And this is the last time we're going to be touching with mechanics, stuff that you probably could have covered in physics 4A, but this is basically the closing chapters on that part. We're going to dive into thermodynamics, which is by Tuesday of next week. I mean, Monday of next week, what am I talking about? This coming Monday. And we're going to spend 4 chapters on it. Then we're going to take the spring break. And after that, we're going to do an exam. Exam is going to cover chapters 12, 15, 16, 17, 18, 19, and 20. Okay, so that is the exam for this section. And then that's where we meet on campus to do the exam. I will tell you up front, the exam is going to emphasize on chapters 19 and 20 by big time. If you don't have at least 1 problem, potentially 2 problems in the exam is not correct, okay, from those 2 chapters. Those 2 chapters are of utmost importance for this class, okay? Chapter 12, maybe, depending, okay, how the exam is going to be structured. Potentially also problems from chapter 15, namely standing waves. Chapter 16, Doppler effect, okay? So these things are important, okay? Chapter 17, which is the next chapter, is very, very important and lays the foundation for what is coming. For chapters basically 18. 18 also is utmost importance too, that we're going to have in it. So for sure, you're going to have a problem from 19 or 20, which is really they're the same. I mean, the ideas extend from one to the other, okay? potentially more, potentially 2 problems from those 2 chapters. But then don't forget problem from 15 combined with 16 on the Doppler effect and standing waves at the same time, okay? And also on stuff from chapters 17 and 18. Chapter 17, thermodynamics, we still have about 5 minutes for this class. Thermodynamics is a science that was discovered backward, okay? It's like driving in reverse when it comes to thermodynamics. Mr. Carnot asked a question. First of all, people knew about heat and they were confused about it. They didn't know what it was. So they gave it a name. They thought it's a fluid of some sort, just like water and all the things. So they gave it the calorific fluid, basically, because you can see it flow from one place to the other. As a matter of fact, you can see the fumes coming out of hot place, for example, hot cup or hot cocoa, for example. You can see what looks like fluid coming out. That's the heat. They thought, okay, that is the calorific fluid, okay? So that's what they thought it was. So they were concerned about it. They tried to understand temperature and things like that. Mr. Carnot, on another side, was an engineer with the French army working on the trains. And basically, he wanted to understand, he asked a question, what is the most efficient engine? Is it the one that runs out of alcohol instead of doing, for example, I don't know, wood? Can I burn some other materials instead? Can I probably bring some cloth and put them inside? Maybe make it out of, instead of iron, maybe aluminum, make it lighter. Would that make it a more efficient engine? So that's a question that he wanted to know. What is the most efficient engine? Okay, he thought hard about this problem. And he said the following, grant me the following. If heat cannot transfer spontaneously on its own without interference, without somebody helping it, from a cold source to a hot source. If you take a cup of coffee that's super hot and a cup that has ice in it, naturally we think that heat will transfer from the hot coffee to the ice. You take ice for hot coffee, for example, and you put in it a cube of ice, the heat will go from the coffee to the cube of ice. From the hot boiling water of the hot coffee to the ice. It cannot go backward. It cannot go from the ice to the hot coffee, because if that happens, the ice becomes colder and the coffee becomes hotter, and that doesn't make sense. Okay. Grant me that this is true all the time. That the fact that hot cannot get any hotter just by the mere fact that it is in contact with a colder source that will at that point get colder. So if this mixture happened to be, he said that the hot will get cooler and the cool will become warmer by virtue of this contact, by this heat exchange on their own. Because somebody might object in the refrigerator. What's going on in the refrigerator? The refrigerator takes something that is cold and you put it in it and it's going to be frozen solid, colder actually at the end, and it's got colder. Well, in this case, that is actually, where did it get that heat from? It extracted it from the cold and make it even colder. But the refrigerator is not a spontaneous process. Refrigerator requires energy, requires work actually, and you pay for it at the end of the month. You pay the bill. What we're talking about spontaneously. If you take an ice cube and put it in front of the contact of the air, it's going to melt on its own. Okay. He said, grant me that, I will give you the most efficient engine. And he was, sure enough, he invented the most efficient engine. That was in the early 1800s. That was now more than 200 years ago. Nobody could still beat his engine. The most efficient engine is that of Carnot. But that, people, when they thought about this problem, they realized, look, this is great what Mr. Carnot ended up with coming with. That is actually outstanding. But we cannot really, because they are now thinking of brand new branch of science called thermodynamics, we cannot really put it at the first law, because there is a far more fundamental principle in here that goes before that, and that is a conservation of energy. So we're going to move the law that Mr. Basically Carnot put and make it as the second law of thermodynamics, and the one that we actually need before it, which is far more fundamental, we call it the first law of thermodynamics. So the first one stated in this process was moved to being second law, and the second one that came in became the first law. That's how the process worked. Several years later, people started working on this problem and exciting about it. There was a far more fundamental question that people needed to answer, and that was the concept of temperature, which is the subject of chapter 17. How do we understand temperature? How do we measure temperature? For that, they realized they needed a law that need to come before the first law. So now the first law is well entrenched. The second law is well entrenched. Now they needed a law that needs to come before the first law. So instead of shifting everything and make the first law discovered that was called 2 and make it into 3, and the second law that was discovered and they made it 1 and move it to 2, and the third law that was basically stated and basically instead of calling it the first law and move everything this way, they called it the zero law of thermodynamics. So again, thermodynamics was basically invented backward. The second law was discovered first, the first law was discovered second, and the third law was discovered, the zeroth law was discovered third, and the order is backward, okay? So we're gonna start with the zeroth law, we're gonna go to the first law, and we're gonna end up with the second law of thermodynamics. So this is, I know it took a minute outside of the time. So hey guys, I'll see you Monday. Please, if you have any questions, let me know, and see you then, okay? Okay, so I'm gonna stop the recording, and I'll see you guys